Every large-scale operation faces the same mathematical dilemma: an infinite number of ways to deploy resources, constrained by strict limits on time, space, and capital. When dealing with massive supply chains or corporate budgets, guessing the best distribution of resources leads to waste. Logistics requires a verifiable result. This diagram illustrates that dilemma on a microscale. You have a fixed pocket budget of 1,000. You want to buy pens for 7 each and erasers for 17. This represents the conflict between capital and your desire to maximize the purchase. This simple transaction is the foundation of linear programming. It's a mathematical framework that models complex relationships as simple linear functions to find the single best possible outcome. By translating chaotic, real-world constraints into strict algebraic rules, we can mathematically calculate the optimal decision. Every linear programming problem begins with decision variables. This text shows them labeled as x and y. These are the specific quantities we have the power to control or adjust, like the number of pens or erasers we choose to buy. Next, we have constraints. These are the hard numerical limits, like factory capacity, available hours, or our fixed budget. They are obstacles that cannot be bypassed. In algebra, these limits are expressed as inequalities. We state that the total resources consumed must be less than or equal to, or greater than or equal to, the absolute limit. Finally, we define the objective function. As you can see at the bottom, this is written as z equals ax plus by. This single equation is our target, what we want to maximize or minimize. To find the true optimal value, we must convert these equations into a geometric map. Optimization relies on accurately plotting the strict boundaries of a complex system in order to visually identify the final surviving choices. Let's build that map. Our goal is to maximize the objective function z equals 3x plus 4y, but we are immediately met with our first strict constraint. X plus y must be less than or equal to 7. To plot this constraint on a graph, we convert the inequality into a standard intercept equation. By dividing the entire equation by 7, we find where the line crosses our axes. Now we have exact coordinates. We plot 7 on the x-axis and 7 on the y-axis, connecting them with a solid boundary line. Because the original constraint was an inequality, less than or equal to 7, we perform an origin test. We plug the coordinates 0, 0 into the equation. Since 0 is indeed less than 7, the statement is true. This means the valid zone lies strictly below the boundary line, stretching down to the origin. This single geometric boundary instantly eliminates half of all mathematical possibilities on the board. We have narrowed our focus to a specific zone of survival. Real-world problems often have multiple limits. Our system has a second constraint. 2x plus 5y must be less than or equal to 20. We perform the same algebraic conversion, isolating the intercepts to reveal an x-intercept of 10 and a y-intercept of 4. We map these new coordinates onto our existing plane, drawing the second boundary line and shading the area strictly beneath it. The system can only exist where all constraints are satisfied at the same time. This geometric overlap creates the feasible solution region, the enclosed polygon trapped near the origin. This diagram contrasts our situation with an unbounded problem. An unbounded graph extends indefinitely, meaning the resources have no upper limit. Our polygon is strictly bounded on all sides, enforcing absolute mathematical limits. Every single coordinate inside this specific polygon satisfies every rule of the system simultaneously. It is the exact map of all survivable choices. The feasible region still contains an infinite number of fractional and decimal coordinates. We cannot test every point manually. This brings us to the core theorem of linear programming. The maximum or minimum value of a linear function will always sit on one of the extreme boundary vertices, or corners, of the feasible region. It will never sit in the middle of the space. We can already identify 3 of these corners simply by looking at our axis intercepts. We have the origin at 0, 0, point A at 7, 0, and point C at 0, 4. But there is a 4th vertex floating in the middle of the quadrant, created by the intersection of our 2 constraint lines. Finding the ultimate optimal state requires locating the exact coordinate where the limits of these multiple constraints intersect. To pinpoint that missing corner, we must step back into the algebra and solve the two intersecting lines as simultaneous equations. This image displays the subtraction method in action. We align the equations and multiply the first constraint by 2. This ensures the x variables in both equations have the same coefficient. By subtracting the modified first equation from the second, the x variables cancel out entirely, allowing us to isolate and solve for y. The algebra dictates that y equals 2. Plugging that back into our first constraint reveals that x equals 5. We now lock in the final vertex. Point B sits precisely at the coordinates 5, 2. The moment those algebraic equations intersect on paper, they dictate the precise geometric limits of the real-world system. With our map fully charted, we return to the original objective function. Z equals 3x plus 4y. This is the profit we are trying to maximize. The final procedural step is to build an evaluation matrix. As shown here, we take our 4 established corner points and plug their coordinates directly into the objective function. Doing nothing at the origin yields 0. Investing strictly along the y-axis at point C yields a value of 16. Moving along the x-axis to point A yields a higher return of 21. But when we test the intersected point B at coordinates 5, 2, the result is 23. This is the highest numerical value the system can generate. These precise calculations isolate the single point that produces the absolute highest possible output, entirely removing any need for guesswork. We can definitively prove why the value 23 is the limit by visualizing the objective function itself. This new line represents our target Z. As we increase our desired profit, the objective line slides outward across the Cartesian plane, moving through the feasible region. The line sweeps across the interior until the exact moment it touches our final vertex, point B. This visual proves that any further increase to the target violates the constraints. Point B is the furthest possible point we can reach while remaining in the feasible region. We turned a set of real-world limitations into strict algebra, mapped it into a geometric cage, and pinpointed the exact corner of maximum potential. Linear programming provides a rigorous method for determining the most efficient outcome in any system defined by linear limits.